This is a macro-level simulation of an eye diagram, the standard measure of signal health in a high-speed digital link. Here, the eye is aggressively collapsing and distorting into random noise. A catastrophic post-silicon failure like this is rarely a manufacturing defect. The mathematical root cause was likely set months earlier in the design phase. In the standard engineering model, teams operate in rigid silos. Digital synthesis, analog layout, and packaging are treated as independent variables, optimized in isolation. To prevent tape-out failures, designers use the integrated methodology shown in this roadmap, Silicon Lifecycle Management, or SLM. This approach requires the architecture phase to mathematically anticipate post-silicon physics, like thermal drift and parasitic coupling, long before the chip is fabricated. This methodology requires a specific pedagogical framework. Dr. S Javed, founder of King Consultants Education, brings over 10 years of experience in the design, layout, and characterization of analog circuits to this problem. The King Consultants curriculum maps directly onto this lifecycle timeline, providing a full-stack, experiential learning approach to integrated circuit design. The engineering challenge today is one of extreme scale. We have to apply this same lifecycle rigor to an autonomous IoT node running on less than 100 microwatts and to a massive server interconnect pushing 40 gigabits per second. Mastering SLM requires a multidisciplinary command of physics. You have to unify first principles analog feedback loops at the transistor level with system-level electromagnetic compliance at the board level. We begin at the earliest phase of the silicon lifecycle. First, core power delivery and substrate-level stability. Before processing any data, it needs electrical equilibrium. This vector topology shows an ultra-low power delivery network for IoT devices. Every nanoampere matters, with deep submicron leakage paths isolated here in red. Zooming in reveals control loops based on negative feedback, adjusting constantly to stabilize the node against variations. A specific architectural solution developed through Dr. Javed's mentorship program addresses this directly. A high PSSR, capless low dropout, or LDO, regulator designed in 90 to 130 nanometer CMOS technology. By utilizing a self-biased recycling folded cascode error amplifier, this LDO architecture manages power highly efficiently without relying on bulky off-chip capacitors. Making these strict architectural choices early prevents a cascade of failures. If the supply voltage ripples at the substrate level, it creates thermal hotspots and power integrity failures that will inevitably interrupt the logic gates downstream. Foundational power architecture acts as the structural bedrock.
Without absolute, predictable stability at the nanowatt level, high-speed synthesis later in the life cycle is mathematically impossible. With power stabilized, we transition to the intermediate phase of SLM, high-speed synthesis, and the scaling of complex clocking trees through the silicon lattice. In multi-gigabit per second environments, the primary bottleneck is timing. You have to actively manage jitter and phase noise across the transceiver blocks to keep the data stream synchronized. This block diagram breaks down phase-locked loops. The LCPLL on the left provides sharp spectral purity but consumes a massive footprint. The ROPLL on the right saves die area but has a noisier phase profile. At 20 GHz, parasitic capacitance begins bleeding the signal away. Scaling up to the data transmission layer introduces the punishing constraints of 40 gigabit per second SerDes design. A serializer-deserializer must accurately reconstruct data across a physical channel without dropping a single bit. You cannot treat the connections between transistors as ideal wires. Wire and interconnect transmission line theory must be embedded directly into the high-speed VLSI design phase to calculate exact signal degradation over the channel. At 40 gigabits per second, logic design and physical layout are indistinguishable. SLM dictates that your high-speed synthesis must account for interconnect parasitics long before you ever reach tape-out. We now zoom out from the bare silicon die to examine the physical packaging and the external environmental interfaces. This 3D model illustrates the core threat to packaged silicon: electromagnetic interference. Radiation fields couple aggressively between adjacent high-speed traces. Parasitic resonance causes a crosstalk spike, corrupting a perfectly clean signal trace and destroying signal integrity at the board level. We see this exact failure mode in extreme frequency applications, specifically 77 GHz car radar. Millimeter wave frequencies require absolute co-design of silicon and the physical package. You cannot build the chip and figure out the casing later. King Consultants dedicates specific coursework to mastering EMI and EMC for electronic systems packaging, because the two materials behave as a single electromagnetic entity. Simultaneously, ADC-based sensor interfaces sitting on the edge of the network must be meticulously shielded and calibrated. They have to translate messy, noisy environmental analog data into pristine digital signals without absorbing EMI corruption. The physical environment is the ultimate arbiter of a chip's viability. Modeling EMC packaging constraints is the final, non-negotiable step of pre-silicon SLM. Pulling back, we see the finalized system-on-chip operating successfully within a broader industrial IoT and agro-IoT framework. The modern VLSI spectrum is incredibly broad, bridging 130-nanometer multi-stage RF energy harvesting rectifiers all the way up to 40 gigabit per second transmission lines. This matrix outlines the unified curriculum at King Consultants, which aims to close the gap between academic theory and industry reality. Advanced analog IC design, high-speed VLSI, and EMI/EMC are mapped directly to sequential SLM ZASMs. Dr. S Javed's expertise across design, layout, and characterization informs this exact progression. It is a full-stack experiential learning approach that treats the silicon lifecycle as a single continuous equation. The siloed engineer designs a block of logic and hopes it survives tape-out. The systems-level engineer applies silicon lifecycle management on day one, anticipating the physics of the final package before drawing the first transistor. Whether you are architecting low-power lab-on-chip sensors or advanced millimeter wave transceivers, anticipating the entire silicon lifecycle during the initial design phase is the only mathematical path to guaranteed silicon success.